The Unix system. In the previous chapters, we examined many operating system principles, abstractions, algorithms, and techniques in general. Now it is time to look at some concrete systems to see how these principles are applied in the real world. We will begin with Unix because it runs on a wider variety of computers than any other operating system. It is the dominant operating system on high-end workstations and servers, but it is also used on systems ranging from notebook computers to supercomputers. It was carefully designed with a clean and despite its age, is still modern and elegant. Many important design principles are illustrated by Unix. Quite a few of these have been copied by other systems. Our discussion of Unix will start with its history and evolution of the system. Then we will provide an overview of the system to give an idea of how it is used. Although graphical interfaces may be easy for beginners, they provide little flexibility and no insight into how the system works. One problem that we will encounter is that there are many versions and clones of Unix, including AIX, BSD, 1BSD, HPUX, Linux, Minix, OSF1, SCO Unix, System V, Solaris, Xenix, and various others, and each of these has gone through many versions. Unix history. Multics, Multiplexed Information and Computing Service. Uniplexed Information and Computing Service. The first version of Unix was developed in 1969 by Ken Thompson of the research group at Bell Laboratories to use an otherwise idle PDP-7. Thompson was soon joined by Dennis Ritchie, and they, with other members of the research group, produced the early versions of Unix. Ritchie had previously worked on the Multics project, and Multics had a strong influence on the newer operating system. Even the name Unix is a pun on Multics. The basic organization of the file system, the idea of the command interpreter or the shell as a user process, the use of a separate process for each command, the original line editing characters, hash to erase the last character and @ to erase the entire line, and numerous other features came directly from Multics. Ideas from other operating systems such as MITS and the XDS 940 system were also used. Ritchie and Thompson worked quietly on Unix for many years. They moved it to a PDP 1120 for a second version. For a third version, they rewrote most of the operating system in the system's programming language C instead of the previously used assembly language. C was developed at Bell Laboratories to support Unix. Unix was also moved to larger PDP-11 models such as the 1145 and 1170. Multiprogramming and other enhancements were added when it was rewritten in C and moved to systems such as the 1145 that had hardware support for multiprogramming. As Unix developed, it became widely used within Bell Laboratories and gradually spread to a few universities. The first version widely available outside Bell Laboratories was version 6, released in 1976. The version number for early Unix systems corresponds to the edition number of the Unix programmer's manual that was current when the distribution was made. The code and the manual were revised independently. In 1978, version 7 was distributed. This Unix system ran on the PDP 1170 and the Interdata 832 and is the ancestor of most modern Unix systems. In particular, it was soon ported to other PDP-11 models and to the VAX computer line. The version available on the VAX was known as 32V. Research has continued since then. History of Unix versions up to 1993. Design principles. Unix was designed to be a time-sharing system. The standard user interface, the shell, is simple and can be replaced by another if desired. The file system is a multi-level tree which allows users to create their own subdirectories. Each user data file is simply a sequence of bytes. Disk files and I/O devices are treated as similarly as possible. Thus, device dependencies and peculiarities are kept in the kernel as much as possible. Even in the kernel, most of them are confined to the device drivers. Unix supports multiple processes. A process can easily create new processes. CPU scheduling is a simple priority algorithm. FreeBSD uses demand paging as a mechanism to support memory management and CPU scheduling decisions. Swapping is used if a system is suffering from excess paging because Unix was originated by Thomson and Ritchie as a system for their own convenience. It was small enough to understand. Most of the algorithms were selected for simplicity, not for speed or sophistication. The intent was to have the kernel and libraries provide a small set of facilities that was sufficiently powerful to allow a person to build a more complex system if needed. Unix clean design has resulted in many imitations and modifications. Although the designers of Unix had a significant amount of knowledge about other operating systems, Unix had no elaborate design spelled out before its implementation. This flexibility appears to have been one of the key factors in the development of the system. Some design principles were involved, however, even though they were not made explicit at the outset. The Unix system was designed by programmers for programmers. Thus, it has always been interactive, and facilities for program development have always been a high priority. Such facilities include the program make, which can be used to check which of a collection of source files for a program need to be compiled and then to do the compiling, and the source code control system, SCCS, which is used to keep successive versions of files available without having to store the entire contents of each step. The primary version control system used by Unix is the Concurrent Version System, CVS, due to the large number of developers operating on and using the code. The operating system is written mostly in C, which was developed to support Unix, since neither Thomson nor Ritchie enjoyed programming in assembly language. Assembly language was also necessary because of the uncertainty about the machines on which Unix would be run. It has greatly simplified the problems of moving Unix from one hardware system to another. From the beginning, Unix development systems have had all the Unix sources available online, and the developers have used the systems under development as their primary systems. This pattern of development has greatly facilitated the discovery of deficiencies and their fixes, as well as of new possibilities and their implementations. It has also encouraged the plethora of Unix variants existing today, but the benefits have outweighed the disadvantages. If something is broken, it can be fixed at a local site. There is no need to wait for the next release of the system. Such fixes, as well as new facilities, may be incorporated into later distributions. The size constraints of the PDP-11 and earlier computers used for Unix have forced a certain elegance. Where other systems have elaborate algorithms for dealing with pathological conditions, Unix just does a controlled crash called panic. Instead of attempting to cure such conditions, Unix tries to prevent them. Where other systems would use brute force or macro expansion, Unix mostly has had to develop more subtle or at least simpler approaches. These early strengths of Unix produced much of its popularity, which in turn produced new demands that challenged those strengths. Unix was used for tasks such as networking, graphics, and real-time operation, which did not always fit into its original text-oriented model. Thus, changes were made to certain internal facilities and new programming interfaces were added. Supporting these new facilities and others, particularly window interfaces, required large amounts of code, radically increasing the size of the system. For instance, networking and windowing both doubled the size of the system. This pattern in turn pointed out the continued strength of Unix. Whenever a new development occurred in the industry, Unix could usually absorb it but remain Unix. Process control. A process is a program in execution. Processes are identified by their process identifier, which is an integer. A new process is created by the fork system call. The new process consists of a copy of the address space of the original process, the same program and the same variables with the same values. Both processes, the parent and the child, continue execution at the instruction after the fork with one difference. The return code for the fork is 0 for the new child process, whereas the non-zero process identifier returned to the parent. Typically, the EXECVE system call is used after a fork by one of the two processes to replace that process's virtual memory space with a new program. The EXECVE system call loads a binary file into memory, destroying the memory image of the program containing the EXECVE system call and starts its execution. A process may terminate by using the exit system call, and its parent process may wait for that event by using the wait system call. If the child process crashes, the system simulates the exit call. The wait system call provides the process ID of a terminated child so that the parent can tell which of possibly many children's terminated. A second system call, wait3, is similar to wait but also allows the parent to collect performance statistics about the child. Between the time the child exits and the time the parent completes one of the wait system calls, the child is defunct. A defunct process can do nothing but exists merely so that the parent can collect its status information. If the parent process of a defunct process exits before a child, the defunct process is inherited by the init process, which in turn waits on it and becomes a zombie process. A typical use of these facilities is shown in figure below. Programmer interface. Like most operating systems, Unix consists of two separable parts, the kernel and the system's programs. We can view the Unix operating system as being layered, as shown in figure below. Everything below the system call interface and above the physical hardware is the kernel. The kernel provides the file system, CPU scheduling, memory management, and other operating system functions through system calls. Systems programs use the kernel-supported system calls to provide useful functions such as compilation and file manipulation. System calls define the programmer interface to Unix. The set of systems programs commonly available defines the user interface. The programmer and user interface define the context that the kernel must support. Most systems programs are written in C, and the Unix Programmer's Manual presents all system calls as C functions. A system program written in C for FreeBSD on the Pentium can generally be moved to an alpha FreeBSD system and simply recompiled even though the two systems are quite different. The details of system calls are known only to the compiler. This feature is a major reason for the portability of Unix programs. System calls for Unix can be roughly grouped into three categories: file manipulation, process control, and information manipulation. The fourth category, device manipulation, but since devices in Unix are treated as special files, the same system calls support both files and devices, although there is an extra system call for setting device parameters. Unix utility programs. A few of the most common Unix utility programs required by POSIX. User interface. Both the programmer and the user of a Unix system deal mainly with the set of systems programs that have been written and are available for execution. These programs make the necessary system calls to support their function, but the system calls themselves are contained within the program and do not need to be obvious to the user. The common systems programs can be grouped into several categories. Most of them are file or directory oriented. For example, the system's programs to manipulate directories are mkdir to create a new directory, rmdir to remove a directory, cd to change the current directory to another, and pwd to print the absolute path name of the current working directory. The ls program lists the names of the files in the current directory. Any of 28 options can ask that properties of the files be displayed also. For example, the -/ option asks for a long listing showing the file name, owner, protection, date and time of creation, and size. The cp program creates a new file that is a copy of an existing file. The mv program moves a file from one place to another in the directory tree. In most cases, this move simply requires a renaming of the file. If necessary, however, the file is copied to the new location and the old copy is deleted. A file is deleted by the rm program, which makes an unlink system call. To display a file on the terminal, a user can run cat. The cat program takes a list of files and concatenates them, copying the result to the standard output, commonly the terminal. On a high-speed CRT display, of course, the file may speed by too fast to be read. The more program displays the file one screen at a time, pausing until the user types a character to continue to the next screen. The head program displays just the first few lines of a file, tail shows the last few lines. Process management. A major design problem for operating systems is the representation of processes. One substantial difference between Unix and many other systems is the ease with which multiple processes can be created and manipulated. These processes are represented in Unix by various control blocks. No system control blocks are accessible in the virtual address space of a user process. Control blocks associated with a process are stored in the kernel. The kernel uses the information in these control blocks for process control and CPU scheduling. Process control blocks. The most basic data structure associated with processes is the process structure. A process structure contains everything that the system needs to know about a process when the process is swapped out, such as its unique process identifier, scheduling information, for example, the priority of the process, and pointers to other control blocks. There is an array of process structures whose length is defined at system linking time. The process structures of ready processes are kept linked together by the scheduler in a doubly linked list, the ready queue, and there are pointers from each process structure to the process's parent, to its youngest living child, and to various other relatives of interest, such as a list of processes sharing the same program code text. The virtual address space of a user process is divided into text, program code, data, and stack segments. The data and stack segments are always in the same address space, but they may grow separately and usually in opposite directions. Most frequently, the stack grows down as the data grow up toward it. The text segment is sometimes, as on an Intel 8086 with separate instruction and data space, in an address space different from the data and stack, and it is usually read-only. The debugger puts a text segment in a read-write mode to allow insertion of breakpoints. Every process text, almost all under FreeBSD, has a pointer from its process structure to a text structure. The text structure records how many processes are using the text segment, including a pointer into a list of their process structures and where the page table for the text segment can be found on disk when it is swapped. The text structure itself is always resident in main memory. An array of such structures is allocated at system link time. The text, data, and stack segments for the processes may be swapped. When the segments are swapped in, they are paged. The page tables record information on the mapping from the process's virtual memory to physical memory. The process structure contains pointers to the page table for use when the process is resident in main memory, or the address of the process on the swap device when the process is swapped. There is no special separate page table for a shared text segment. Every process sharing the text segment has entries for its pages in the process's page table. Information about the process needed only when the process is resident, that is, not swapped out, is kept in the user structure or use structure rather than in the process structure. The use structure is mapped read-only into user virtual address space so user processes can read its contents. It is writable by the kernel. The use structure contains a copy of the process control block or PCB, which is kept here for saving the process's general registers, stack pointer, program counter, and page table base registers when the process is not running. There is space to keep system call parameters and return values. All user and group identifiers associated with the process, not just the effective user identifier kept in the process structure, are kept here. Signals, timers, and quotas have data structures here. Of more obvious relevance to the ordinary user, the current directory and the table of open files are maintained in the user structure. Every process has both a user and a system mode. Most ordinary work is done in user mode, but when a system call is made, it is performed in system mode. The system and user phases of a process never execute simultaneously. When a process is executing in system mode, a kernel stack for that process is used rather than the user stack belonging to that process. The kernel stack for the process immediately follows the user structure. The kernel stack and the user structure together compose the system data segment for the process. The kernel has its own stack for use when it is not doing work on behalf of a process, for instance, for interrupt handling. The fork system call allocates a new process structure with a new process identifier for the child process and copies the user structure. There is ordinarily no need for a new text structure as the processes share their text. The appropriate counters and lists are merely updated. A new constructed and new main memory is allocated for the data and stack segments of the child process. The copying of the user structure preserves open file descriptors, user and group identifiers, signal handling, and most similar properties of a process. Figure illustrates how the process structure is used to find the various parts of a process. The vfork system call does not copy the data and stack to the new process. Rather, the new process simply shares the page table of the old one. A new user structure and a new process structure are still created. A common use of this system call occurs when a shell executes a command and waits for its completion. The parent process uses vfork to produce the child process because the child process wishes to use an execve immediately to change its virtual address space completely. There is no need for a complete copy of the parent process. Such data structures as are necessary for manipulation pipes may be kept in registers between the vfork and the execve. Files may be closed in one process without affecting the other process, since the kernel data structures involved depend on the user structure, which is not shared. The parent is suspended when it calls vfork until the child either calls execve or terminates, so that the parent will not change memory that the child needs. When the parent process is large, vfork can produce substantial savings in system CPU time. However, it is a fairly dangerous system call since any memory change occurs in both processes until the execve occurs. An alternative is to share all pages by duplicating the page table, but to mark the entries of both page tables as copy on write. Protection bits are set to trap any attempt to write in these shared pages. If such a trap occurs, a new frame is allocated and the shared page is copied to the new frame. The page tables are adjusted to show that this page is no longer shared and therefore no longer needs to be write protected, and execution can resume. An execve system call creates no new process or user structure, rather the text and data of the process are replaced. Open files are preserved, although there is a way to specify that certain file descriptors are to be closed on an execve. Most signal handling properties are preserved, but arrangements to call a specific user routine on a signal are cancelled for obvious reasons. The process identifier and most other properties of the process are unchanged. CPU scheduling. CPU scheduling in Unix is designed to benefit interactive processes. Processes are given small CPU time slices by a priority algorithm that reduces to round-robin scheduling for CPU-bound jobs. Every process has a scheduling priority associated with it. Large numbers indicate lower priority. Processes doing disk I/O or other important tasks have priorities less than P0 and cannot be killed by signals. Ordinary user processes have positive priorities and thus are less likely to be run than is any system process, although user processes can set precedence over one another through the nice command. The more CPU time a process accumulates, the lower, more positive its priority becomes, and vice versa. This negative feedback in CPU scheduling makes it difficult for a single process to take all the CPU time. Process aging is employed to prevent starvation. Older Unix systems used a 1-second quantum for the round-robin scheduling. FreeBSD reschedules processes every 0.1 second and recomputes priorities every second. The round-robin scheduling is accomplished by the timeout mechanism, which tells the clock interrupt driver to call a kernel subroutine after a specified interval. The subroutine to be called in this case causes the rescheduling and then resubmits a timeout to call itself again. The priority recomputation is also timed by a subroutine that resubmits a timeout for itself. There is no preemption of one process by another in the kernel. A process may relinquish the CPU because it is waiting on I/O or because its time slice has expired. When a process chooses to relinquish the CPU, it goes to sleep on an event. The kernel primitive used for this purpose is called sleep, not to be confused with a user-level library routine of the same name. It takes an argument which is by convention the address of a kernel data structure related to an event that the process wants to occur before that process is awakened. When the event occurs, the system process that knows about it calls wakeup with the address corresponding to the event, and all processes that had done a sleep on the same address are put in the ready queue to be run. For example, a process waiting for disk I/O to complete will sleep on the address of the buffer header corresponding to the data being transferred. When the interrupt routine for the disk driver notes that the transfer is complete, it calls wakeup on the buffer header. The interrupt uses the kernel stack for whatever process happened to be running at the time, and the wakeup is done from that system process. The process that actually does run is chosen by the scheduler. Sleep takes a second argument, which is the scheduling priority to be used for this purpose. This priority argument, if less than P0, also prevents the process from being awakened prematurely by some exceptional event such as a signal. When a signal is generated, it is left pending until the system half of the affected process next runs. This event soon, since the signal normally causes the process to be awakened if the process has been waiting for some other condition. No memory is associated with events. The caller of the routine that does a sleep on an event must be prepared to deal with a premature return, including the possibility that the reason for waiting has vanished. Race conditions are involved in the event mechanism. If a process decides, because of checking a flag in memory for instance, to sleep on an event, and the event occurs before the process can execute the primitive that does the actual sleep on the event, the process sleeping may then sleep forever. We prevent the situation by raising the hardware processor priority during the critical section so that no interrupts can occur, and thus only the process desiring the event can run until it is sleeping. Hardware processor priority is used in this manner to protect critical regions throughout the kernel and is the greatest obstacle to porting Unix to multiple processor machines. However, this problem has not prevented such porting from being done repeatedly. Many processes, such as text editors, are I/O bound and usually will be scheduled mainly on the basis of waiting for I/O. Experience suggests that the Unix scheduler performs best with I/O bound jobs, as can be observed when several CPU bound jobs, such as text formaters or language interpreters, are running. However, the negative feedback property of the priority scheme provides some long-term scheduling in that it largely determines the long-term job mix. Medium-term scheduling is done by this swapping mechanism. Memory management. Much of Unix's early development was done on a PDP-11. The PDP-11 has only 8 segments in its virtual address space, and the size of each is almost 8,192 bytes. The larger machines, such as the PDP-1170, allow separate instruction and address spaces, effectively doubling the address space and number of segments, but this address space is still relatively small. In addition, the kernel was even more severely constrained due to dededication of one data segment to interrupt vectors, another to point at the per-process system data segment, and yet another for the Unibus system I/O bus registers. Further, on the similar PDP-11s, total physical memory was limited to 256 KB. The total memory resources were insufficient to justify or support complex memory management algorithms. Thus, Unix swapped entire process memory images. Berkeley introduced paging to Unix with 3BSD. VAX 4.2 BSD is a demand-paged virtual memory system. Paging eliminates external fragmentation of memory. Internal fragmentation still occurs, but it is negligible with a reasonable small page size. Because paging allows execution with only parts of each process in memory, more jobs can be kept in main memory and swapping can be kept to a minimum. Demand paging is done in a straightforward manner. When a process needs a page and the page is not there, a page fault to the kernel occurs, a frame of main memory is allocated, and the proper disk page is read into the frame. There are a few optimizations. If the page needed is still in the page table for the process, but has been marked invalid by the page replacement process, it can be marked valid and used without any I/O transfer. Pages can similarly be retrieved from the list of free frames. When most processes are started, many of their pages are pre-paged and are put on the free list for recovery by this mechanism. Arrangements can also be made for a process to have no pre-paging on startup, but that is seldom done, as it results in more page fault overhead, being closer to pure demand paging. FreeBSD implements page coloring with paging queues. The queues are arranged according to the size of the process's L1 and L2 caches, and when a new page needs to be allocated, FreeBSD tries to get one that is optimally aligned for the cache. If the page has to be fetched from disk, it must be locked in memory for the duration of the transfer. It ensures that the page will not be selected for page replacement. Once the page is fetched and mapped properly, it must remain locked if raw physical I/O is being done on it. The page replacement algorithm is more interesting. BSD uses a modification of the second chance clock algorithm. The map of all non-kernel main memory, the core map or CMAP, is swept linearly and repeatedly by a software clock hand. When the clock hand reaches a given frame, if the frame is marked as being in use by some software condition, for example, if physical I/O is in progress using it, or if the frame is already free, the frame is left untouched and the clock hand sweeps to the next frame. Otherwise, the corresponding text or process page table entry for this frame is located. If the entry is already invalid, the frame is added to the free list. Otherwise, the page table entry is made invalid but reclaimable, that is, if it has not been paged out by the next time it is wanted, it can just be made valid again. BSD Tahoe added support for systems that implement the reference bit. On such systems, one pass of the clock hand turns the reference bit off, and a second pass places those pages whose reference bits remain off onto the free list for replacement. Of course, if the page is dirty, it must first be written to disk before being added to the free list. Page outs are done in clusters to improve performance. There are checks to make sure that the number of valid data pages for a process does not fall too low and to keep the paging device from being flooded with requests. There is also a mechanism by which a process can limit the amount of main memory it uses. The LRU clock hand scheme is implemented in the page daemon, which is process 2. Remember that the swapper is process 0 and init is process 1. This process spends most of its time sleeping, but a check is done several times per second, scheduled by a timer to see if action is necessary. If it is, process 2 is awakened. Whenever the number of free frames falls below a threshold, lots free, the page daemon is awakened. Thus, if there is always a large amount of free memory, the page daemon imposes no load on the system because it never runs. File system. The Unix file system supports two main objects, files and directories. Directories are just files with a special format, so the representation of a file is the basic Unix concept. Blocks and fragments, inodes, directories, mapping a file descriptor to an inode, disk structures, implementations, layout and allocation policies. Some important directories found in most Unix systems. Input-output system. One of the purposes of an operating system is to hide the peculiarities of specific hardware devices from the user. For example, the file system presents a simple, consistent storage facility, the file, independent of the underlying disk hardware. In Unix, the peculiarities of devices are also hidden from the bulk of the kernel itself by the I/O system. The I/O system consists of a buffer caching system, general device driver code, and drivers for specific hardware devices. Only the device driver knows the peculiarities of a specific device. The major parts of the I/O system are diagrammed in figure below. There are three main kinds of I/O in FreeBSD: block devices, character devices, and the socket interface. The socket interface, together with its protocols and network interfaces. Block devices include disks and tapes. Their distinguishing characteristic is that they are directly addressable in a fixed block size, usually 512 bytes. A block device driver is required to isolate details of tracks, cylinders, and so on from the rest of the kernel. Block devices are accessible directly through appropriate device special files such as /dev, /rp0, but they are more commonly accessed indirectly through the file system. In either case, transfers are buffered through the block buffer cache, which has a profound effect on efficiency. Character devices include terminals and line printers, but also include almost everything else except network interfaces that does not use the block buffer cache. For instance, /dev/mem is an interface to physical main memory, and /dev/null is a bottomless sink for data and an endless source of end-of-file markers. Some devices, such as high-speed graphics interfaces, may have their own buffers or may always do I/O directly into the user's data space. Because they do not use the block buffer cache, they are classed as character devices. Terminals and terminal-like devices use CLIS, which are buffers smaller than those of the block buffer cache. Block devices and character devices are the two main device classes. Device accessed by one of the two arrays of entry points. One array is for block devices, the other is for character devices. A device is distinguished by a class, block, or character and a device number. The device number consists of two parts. The major device number is used to index the array for character or block devices to find entries into the appropriate device driver. The minor device number is interpreted by the device driver as, for example, a logical disk partition or a terminal line. A device driver is connected to the rest of the kernel only by the entry points recorded in the array for its class and by its use of common buffering systems. This segregation is important for portability and for system configuration. Inter-process communication. Although many tasks can be accomplished in isolated processes, many others require inter-process communication. Isolated computing systems have long served for many applications, but networking is increasingly important. Furthermore, with the increasing use of personal workstations, resource sharing is becoming more common. Inter-process communication has not traditionally been one of Unix's strong points. Sockets. The pipe is the IPC mechanism most characteristic of Unix. A pipe permits a reliable unidirectional byte stream between two processes. It is traditionally implemented as an ordinary file with a few exceptions. It has no name in the file system, being created instead by the pipe system call. Its size is fixed, and when a process attempts to write to a full pipe, the process is suspended. Once all data previously written into the pipe have been read out, writing continues at the beginning of the file. Pipes are not true circular buffers. One benefit of this small size, usually 4096 bytes, of pipes is that pipe data are seldom actually written to disk. They usually are kept in memory by the normal block buffer cache. In FreeBSD, pipes are implemented as a special case of the socket mechanism. The socket mechanism provides a general interface not only to facilitate facilities such as pipes, which are local to one machine, but also to networking facilities. Even on the same machine, a pipe can be used only by two processes related through use of the fork system call. The socket mechanism can be used by unrelated processes. A socket is an endpoint of communication. A socket in use usually has an address bound to it. The nature of the address depends on the communication domain of the socket. A characteristic property of a domain is that processes communicating in the same domain use the same address format. A single socket can communicate in only one domain. Socket types. There are several socket types which represent classes of services. Each type may or may not be implemented in any communication domain. If a type is implemented in a given domain, it may be implemented by one or more protocols which may be selected by the user. Stream sockets. These sockets provide reliable, duplex, sequenced data streams. No data are lost or duplicated in delivery, and there are no record boundaries. This type is supported in the Internet domain by TCP. In the Unix domain, pipes are implemented as a pair of communicating stream sockets. Sequenced packet sockets. These sockets provide data streams like those of stream sockets, except that record boundaries are provided. This type is used in the Xerox AFNS protocol. Datagram sockets. These sockets transfer messages of variable size in either direction. There is no guarantee that such messages will arrive in the same order they were sent, or that they will be unduplicated, or that they will arrive at all, but the original message or record size is preserved in any datagram that does arrive. This type is supported in the Internet domain by UDP. Reliably delivered message sockets. These sockets transfer messages that are guaranteed to arrive and that otherwise are like the messages transferred using datagram sockets. This type is currently unsupported. Raw sockets. These sockets allow direct access by processes to the protocols that support the other socket types. The protocol's accessible example, in the Internet domain, it is possible to reach TCP, IP beneath that, or an Ethernet protocol beneath that. This capability is useful for developing new protocols. Network support. Almost all current Unix systems support the UUCP network facilities, which are mostly used over dial-up telephone lines to support the UUCP mail network and the Usenet news network. These are, however, rudimentary networking facilities. They do not support even remote login, much less remote procedure calls or distribute file systems. These facilities are almost completely implemented as user processes and are not part of the operating system itself. The networking framework in FreeBSD is more generalized than is either the ISO model or the ARM, although it is most closely related to the ARM, as shown in figure below. There are only 4 protocol layers in the ARM. Process applications. This layer subsumes the application, presentation, and session layers of the ISO model. Such user-level programs as the File Transfer Protocol (FTP) and Telnet remote login exist at this level. Host-to-host. This layer corresponds to ISO's transport and the top part of its network layers. Both the Transmission Control Protocol (TCP) and the Internet Protocol (IP) are in this layer, with TCP on top of IP. TCP corresponds to an ISO transport protocol and IP performs the addressing functions of the ISO network layer. Network interface. This layer spans the lower part of the ISO network layer and the entire data link layer. The protocols involved here depend on the physical network type. The ARPANET uses the IMP host protocols, whereas an Ethernet uses Ethernet protocols. Network hardware. The ARM is primarily concerned with software, so there is no explicit network hardware layer. However, any actual network will have hardware corresponding to the ISO physical